All right, we've got the concepts of force analysis introduced clearly. We've got Newton's 3 laws of motions carefully stated. You can't learn this stuff without doing problems. You just can't learn physics without doing problems. You can't learn baseball without taking some at-bats and some grounders. You can't learn an instrument without playing. And physics is really a skill. So that frees you up. Realize that you can't just keep reading and reading and reading without doing problems. Problems are puzzles. They force you to pull these ideas together. So as you do more problems, more subtle problems, your intuition is going to be jarred a little, and you'll refine it and come back. And so you'll come back to this and understand it even more deeply when you really get it. Wow, it's going to be great. Work on your speed, it matters. So a couple of quick points before we do force analysis method, and then we'll jump into doing it. Force analysis, reminders and subtleties. Force. This is a big confusion that people have, and it can be an unconscious confusion. Right? Our net force is not directly related to velocity. So maybe there's a huge net force. I don't know if I'm going fast or not. It is directly related to acceleration, but you know from kinematics, acceleration is not directly related to velocity. Usually we have a highest acceleration in a car when we're going slow, or we're from rest, getting up to speed, getting onto the freeway. Once we're going fast, we want small acceleration. Small acceleration means small net force. Large acceleration means large net force. Velocity, don't make an assumption about that, okay? So it's not directly tied. It's related through the kinematics, but not directly. So keep that in mind. Don't go getting that confused. Force magnitude in newtons or pounds usually. A newton about a quarter pound. Keep that in mind. I want to point something out here though. Mass is in kilograms in the SI system, also MKS. Or grams is fine. That G is not free flight acceleration. It's not the 9.8 meter per second squared, right? So we have letters that mean different things. Just be careful with that. Or slugs, for that matter. Now, force, as you know, is an interaction. It's not mass. Mass is a property matter has. It's something deep there. But force is not it. So, newtons are not the same as kilograms. You can't convert between the two. You can't convert between meters and seconds. You can't do that. Newtons and kilograms, there isn't a direct conversion. We'll talk about that. Pounds, like newtons, are not kilograms, and yet across the globe people talk about weight in kilograms. They're shortcutting something. So it's not really technically correct. They get away with it because you're working on Earth all the time. We'll talk about that when we talk about the force of gravity. So weight is really not in kilograms. We'll get to that later. All right, let's get on with it. Force analysis steps. We're going to do problems. Lots of problems. If you train these steps, it'll take you into more awareness of the physics. Problem solving. Think physics. Write down every bit that you know, and see how the puzzle pieces come together. Number 1, decide to use force analysis if it's useful. If it's not useful, fine. If you're going to do kinematics, do kinematics. If you're going to do energy, do energy. If you're going to do momentum, do momentum. If you're going to do force and energy, do them one at a time. So first you have to make a decision, and you're going to have choices. Then, R, choose the object to look at, your receiver. Now that can vary, Am I looking at the blue pen or the whatever color that is pen, or my hand, or what are you looking at? So choose the object, receiver. You can call it C if it's a car, B if it's a boat, whatever, name it. Next, now that you've selected, now you might go back and look at other things, but for the time being, just focus on one object, right? It could be a group object. I could treat this whole thing as my object, remember, or one, or the other. Okay, so select something and just see where it goes. Draw a free body diagram for R. So draw R as a dot, because we're not worrying right now about rotations, twisting things, rolling, spinning. That will be later. So draw it as a dot, or a rectangle, or a circle. Don't spend too much time making pretty pictures. It's fun, but just get to it. You want to get the essence here. Then the force vectors on R. Once you've drawn your R, draw in all the force vectors, arrows, on R. All the pushes and pulls on that thing from other things. How do you see them? Well, you look for contact forces and non-contact. So you just look at R and say, what is touching R? So that's pretty easy. I mean, you could ask a kindergartner, what's touching this? Well, my hand. Right, that's it. You know, what's touching this pen? The blue pen. Okay, now the blue pen and the green pen. Okay, fine. So what's touching it? Now there's another question. I kind of like this. Non-contact forces. Well, there it went. Gravity. Something pulled that right out. Earth pulled it out. Non-contact forces. So for now, gravity is going to be our only non-contact force. We'll get into electric and magnetic force in time, but that's too much. So you simply look at R, say what's touching it, and then throw in gravity, right? Force of gravity. Great. Draw them all in. You don't care at this point about the other objects. In other words, if I'm looking at green, then purplish is touching it. And if I'm looking at the motion of green, I just look at R. I don't care about the back force. Newton's third law might come into play. But for now, we're summing up the forces on that guy. Okay, cool. Label all the force vectors. Now, this takes a little more time, but it will train you, and it'll catch you. You know, you go, yeah, 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 and you go, yeah, 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 right over the mistake. So if you do this, you'll really retrain your thinking. The little subtle points, the points that get you stuck and hit the wall and confuse and lose points on exam and everything. If you label, work on hand speed, right, quickly, all the force vectors, by filling in the blanks this way, you really train yourself. The force, the type, gravity, normal, friction, tension. From, put in the object. Force of gravity from Earth. On the car, on the boat, on the block, right? Whatever. Now, for this, we're doing the free body diagram for object R. So here, all these forces are on R. I don't care about what happens, what R does to them. Okay, everybody cool? Decide to do it. Just realize you've got choices. Once you see that, that's going to be pretty good. Choose your object. What are you focusing on? Free body diagram for that guy. All the forces. Just stick them in. Label them. From what? On that thing. All right, cool. Now what do? You got a bunch of vectors. You got a picture. All right. Well, let's come over here. Almost there. And what you need to do is divide and conquer. If it's one-dimensional problem, fine. Call one direction plus, the other direction negative, and you're good. You don't even need all this vector notation and all that stuff. But the world isn't one-dimensional. In fact, it's three-dimensional. But two dimensions will give us the method adequately. So we're going to choose a coordinate system. Again, that's a pretty advanced thing. I mean, you choose which way is plus or minus, and which way is x or y, so that your math is easier, and so that you're clearer thinking about the process. So how do you do it? A good guideline, in most cases, if not all, is that you usually choose one direction parallel to the acceleration or opposite to the acceleration, negatively. And then the perpendicular direction, A is 0, and I'll show you why. Now, not always. You can do it otherwise. Then A would have components. You'd have an AX and an AY. But in this case, you've only got acceleration one direction and 0 the other way. So for example, show and label that. So on next to your free body diagrams, please do this. It'll save you so much time. There's too many puzzle pieces. You got to keep them straight. Do this. If I choose that way positive, maybe it's because the acceleration is down A. I could choose that way positive, and the acceleration is A. If I don't know what it is, put it in as a symbol. Some things you won't know the numbers for, and even if you do, put it in as a symbol first and deal with the numbers later. If all the acceleration is this way, then the perpendicular direction, AY is 0, and we'll see why that's a beautiful thing. Or maybe free flight, where horizontally the acceleration is 0, and vertically the acceleration is down with a value of g. Not grams, right? But free flight acceleration of g. Or you can choose down positive if it never goes up. Whatever, it all works. But if you draw this, then you can reference this in the next step, which is to say your force component table. Now this is just any vector addition, you're going to do this kind of table. We did it for displacements, we can do it for any vectors. It really helps organize your thinking, and you are in training, right? If you're really good at this, maybe you can keep it organized. But a table will truly help, and it'll help catch your mistakes. If you do that on an exam, and you have a little mistake here, but everything else is right, well, you're due a lot of points. Force component table, break every force that we showed into x and y components. Use your sketch and your trig. So how do you do it? Polar form is the amount, or magnitude also called, and the direction, the arrow.